So good afternoon, everyone. This is Amrinder Singh from CPO Innovation, your host for today's webinar on applying green aviation concept and optimization model of weight distribution and fuel consumption. So the major takeaway of today's webinar will be the future of aviation sector, the problems faced by the sector, the real threat of greenhouse gas emissions problem, and the financial benefits of having optimized weight distribution on both long run and short run terms, and in relation to greenhouse gas emissions, followed by a real life case study on Egypt Air Aviation companies facilitated located on Cairo International Airport. Right. So now I would like to take pleasure to introduce the speaker of today's webinar, Mr. Kiroz Risk. Mr. Kiroz Risk is a supply chain professional from Cairo, Egypt. Kiroz works as an optimization analyst and a regional representative at EOS Track Company and a gold supply chain ambassador at Global Supply Chain Council. So now, with no further delay, I would like to invite Mr. Kiroz Risk to take the webinar. Kiroz, over to you.
Thanks a lot, Amrinder, for the great introduction. It's already a great honor for me to join this webinar powered up by CPO Innovation. Welcome to all the audience, and I hope that today's topic can be rich with benefits. So today we'll be discussing a problem that we are all facing. The amount of greenhouse gas emissions are increasing globally. We all, from different countries, we are all trying to reduce these emissions from different industries, from different sectors of transportation or different operations. So today we'll be focusing our efforts on the aviation sector. We are having some proposed solution. We are going to define the problem in a wider and more broad way. We are going to discuss different aspects of the problems. So today's webinar is going to be titled Applying Green Aviation Concept. It's an optimization model of weight distribution and its effect on the fuel consumption. Thanks a lot for Armindar for the introduction. I'm a TEDx speaker at TEDx Haiwan University. You already know where do I work, so let's go straight to the topic. So our timeline is very simple. We are going to start off with an introduction. It's a general problem definition. What exactly is the problem? How big is it? How can we solve it? What are the factors affecting it? Then we'll be highlighting some important trials and effective trials made by different players in the aviation sector, by various global entities across the globe, as they try to reduce the greenhouse emissions throughout optimizing different operations across the chain of the aviation sector. Then we'll be presenting two different approaches. We'll be applying these approaches, a mass model and the effect of biodiesel, different factors, on real-life case study applied on a real-life company called Egypt Air. So let's start this off with a simple introduction. The aviation sector is one of the largest fields of transport. It has been growing rapidly, actually, through the past years. In this report that was released by the IATA last June, you can see that in 2004, around 2,000 million passengers were transported globally using airplanes. Yet, last June, only in the mid-year, around 4,500 million passengers were already transported using airplanes. So this field is growing up in a very, very high pace. But actually, as this sector grows in size, the amount of CO2 emissions and the amount of problems that it faces grows up with it. In this graph that was released by C-Roads. C-Roads is an application released by the United Nations and different research centers and universities that measures the amount of CO2 emissions, peak year, current emissions, and tries to predict the amount of emissions each year throughout the coming 80 years, 100 years. So according to these reports, the amount of CO2 emissions is just going to get its peak by 2100, which is very, very unacceptable. It's contradicting with our SDGs, with our national plans, so we have to do extra efforts within this scope to have better future for us and for our children. So, according to the World Resources Institute, the aviation sector is responsible for about 2% of the global greenhouse gas emissions. The percentage is increasing in a very high pace, just as the size of this sector, and there is limited progress in reducing it. So here we are, and that's why we are discussing this specific topic today. Throughout the research, we collected a number of trials to solve the problems by various players in the aviation industry. Between the start point of the aviation industry in 1903, the Wright brothers, and June 2019. So our timeline starts with 1903, the Wright brothers with their successful first ever sustained human flight. This was the launching point for this huge sector of transportation. Then on 1997, the Kyoto Protocol was established in order to reduce the amount of greenhouse gas emissions globally with cooperation with national governments and global entities, but it suspended the aviation sector to be managed by the International Civil Aviation Organization, the ICAO. In 2003, the United Nations government launched the Vision 100th Century of Aviation Reauthorization, which aimed to reducing the overall emissions of airports by providing financial support to these airports and to the national airlines, and by convincing sponsors to finance the whole project as well. So they are trying to get the different players in the aviation sector more keen, more excited on investing their money in replacing the old planes with new modern planes with better engines, fewer emissions, try to invest more in optimizing their day-to-day operations. Yet in 2010, the base point of our research was planted by Imperial College London as they introduced the continuous descent operations. The CDO is not a technology, actually it's just a technique that has been taught to the pilots to teach them the optimal way to take off and to land using the optimal altitude, the optimal speed, the optimal angle, so that we can minimize the amount of fuel burn, the amount of CO2 emitted, gases emitted. So these factors have very, very a huge weight and effect on this problem. This CDO was actually applied and used by different airports across the globe. Birmingham Airport applied the CDO, and the results were fascinating. 13,000 tons of CO2 this year, just because of the CDO. Zurich Airport in Switzerland, they applied this CDO technique, and they started planting electric units instead of powering up the plane engines, which saved them up to 30 tons of CO2 that year. Also, London Heathrow's airport, which is the world's most busy airport, they introduced the CDO, and they started optimizing extra operations such as preconditioned air instead of powering up the plane engines and consuming extra fuel for secondary reasons. So they were able to save around 100,000 tons of CO2 that year, which is a huge number and a huge result. Also, in 2012, the Indian researchers Devinder Kumar and Anshul Sharma They continued this research by developing an optimization model regarding the effect of taking off, landing, and aviator attitude and the speed and cruise mode on the fuel burned and relatively on the amount of CO2 emitted because of this amount of fuel burned. In 2019, the Chinese researchers, Ziping Zhu and John Pei, they even worked the extra mile. They defined a new approach to reduce the amount of fuel consumed by affecting many flight factors, such as the weight, which we handled in our research, the flight altitude, the velocity factors, and their strong relation on the fuel consumption and relatively to the amount of greenhouse gas emissions. So, we have the SDGs, the Sustainable Development Goals of the United Nations. We are supposed to have 20% fewer greenhouse gas emissions emitted from the aviation sector by 2020, lower than those ratios of 2013, but actually are very far away from these ratios. According to the World Resources Institute, there is insufficient progress and most likely are not going to achieve this goal by 2020. So we still have the chance to achieve this goal by 2030, 2050. So here we are trying to propose different solutions, different approaches to solve such a major problem that we face globally. Yet we cannot move on, we cannot mention the global trials made by different players without highlighting the main players in this sector, which are the airlines, companies. Actually, the airlines were the most active and the most keen and enthusiastic players who tried a wide variety of solutions to reduce the amount of CO2. We have various examples such as Qantas Australian Airlines, the Japanese airlines, Lufthansa Airlines. These three have invested millions of dollars and they were able to bear the burden of losing millions of dollars because of different trials of using biofuels or using different operations, investing in new planes. Actually, different airlines started creating trial trips for more than 13 hours. The planes were only operating with biofuels, even if that is going to harm the engine, yet they wanted to try it. So yeah, we have to raise the hat for these guys. So before we move on, and before going to the core of our webinar, which are the proposed solutions, I have to remind you with the Tech Supply Chain Conference 2019, it will be taking place on September 19 and September 20. It's very, very interesting conference. The ticket only costs around 300 rubric. The key themes and the discussed topics are very, very interesting. The artificial intelligence, fuel organizations, the preparing for the unexpected, intelligence, artificial and human balancing, and cost optimization, which is kind of linked to today's webinar. So hurry up and register now. You can put your name and details in the comment section. So we would love to get back to you then. So here we go. This is our real starting point for this webinar. The first proposed approach, which is a water tank optimization problem. There is an equation that represents the real relation between the weight and fuel factor, the fuel burning factors, the amount of greenhouse gas emissions. So these three are very, very linked. So approximately for every 1 ton, 1,000 kilograms extra weight for the plane, around 300 liters of fuel are burned each hour. Also, for each ton of fuel burned, around 2.64 tons of CO2 are emitted for each hour. So they are related. Today, we'll be applying this equation on a real-life case study, which is Egypt Air. Egypt Air is one of the world's pioneer airlines. It's Egypt's national airline. It was established in May 1932. They are a member of the Star Alliance network, which is the largest airline alliance in the world. They have a huge number of trips each day, so there will be a perfect example for us to measure our proposed solutions on them. Our research plan started on a field visit to Cairo International Airport, to be more specific to the Egypt Air facilities on the Cairo International Airport, to gather all the required data and to observe closely all the operations to be able to select which operation exactly contribute more or the most to the amount of greenhouse gas emissions, which operations that requires the most optimization, the most effort. So we chose a small trip, a short trip between Cairo and Jeddah. It's almost 2 hours trip. It's almost 1,215 kilometers, so it's a very short one. But we selected this trip specifically because it has huge seasonality factor. Egypt Air flies about 2,365 trips annually between Cairo and Jeddah. So this is a huge number of trips each year. Why is that? The reason that there is a huge number of trips and huge seasonality index for this specific trip, because Muslims tend to fly each year in different occasions, different timings per year, from Cairo to Saudi Arabia to pray. So there is huge seasonality on this trip. So we thought it would be the best trip to be able to measure our proposed solutions. On further observation, we found out that there are 3 main plane models that flies on this specific trip, which are the small Boeing 737-800 plane, 2 large Airbus planes, A330-200 and Airbus 330-300 planes, with an emergency plane, a small Airbus 321-200 plane that we neglected in our research since it flies rarely in cases of emergency or demand surge or something, so we cannot measure it accurately. So, on close observation on the daily operations of this specific trip, on the plane flying on this specific trip, we found out that there is a rule that Egypt Air created, that any plane that flies from Cairo to Jeddah has to get its water tank filled by 50% of its capacity, regardless for the capacity of passengers, the consumption, the departure times, and all of these factors. Yet the other problem was that all the Boeing 737-800 planes, the water tank sensor beneath the plane is malfunctioning. So they are filling it by 100% for all the trips flying from Cairo to Jeddah, which is not perfectly right. Also, the 2 large Airbus planes, they are getting filled by 60% instead of 50%. Why? Because they believe that these planes hold a huge number of passengers, so the consumption might be high, so they need to have extra water to make sure that water does not run out and customers stay delighted. So this is not actually right as well. So we were able through the month to collect around 79 planes, the data for around 79 planes with different data types. So let me zoom in here. Okay, give me a moment. Okay, so we were able to gather the departure time, the plane model, the actual water tank filled capacities, the maximum water tank capacities, the amount of used water, the amount of unused water in liters, of course, the maximum passenger capacity, and the actual capacity for each plane. the consumption per passenger, the extra consumed fuel according to the amount of unused water, the weight of the amount of unused water according to the equation that we mentioned before, the cost of this extra unused, the extra consumed fuel per hour and per trip, and the amount of CO2 emissions emitted because of this extra burned fuel. So mainly that was the data, this was the data that we collected throughout the months for about 80 planes. Then we started formulating our mass model. First of all, we defined our objective function. So our objective was to minimize the cost of extra burned fuel because of the amount of unused water using the term Xij cask. Let us not rush this and discuss it in a more brief way. So the X is a value, is the number, it's the variable that we are going to optimize. The I is the fleet time. What hour exactly is this plane going to take off? So Egypt Air has 13 departure times each day. So we have 13 I's for this specific term. As for the J is the fleet type. Egypt Air, as I mentioned before, has 3 main plane models that flies on this trip. So there are 3 J in this term. Let us keep the CASK for 5 more minutes. We are going to go deeply in discussing this term. So after defining our objective function, we started mentioning our constraints. We have the first constraint, for example, it's x11 plus x12 plus x13 equal 1. This means that the first plane at the first departure time plus the second plane, the first plane at the second departure time plus the first plane at the third departure time equals 1. So only one plane can take off at the first departure time. Similar for the same thing is applied on the 13 constraints. Also, Egypt Air has limitations regarding the number of planes. There are 9 Boeing planes, 2 Airbus 200 planes, and 2 Airbus 300 planes. And for sure, our mass model should be binary. The results should be binary. So here we can discuss the CASK. Getting back to this term, the CASK is the cost of available seat kilometer. So it's the whole cost, the complete cost related to the passenger sitting on the plane for each seat moving for 1 kilometer. That's the broad definition of the CASK. Here in this research, we are measuring specific costs. So we're holding everything constant, and we are defining the CASK as the cost of extra burned fuel because of the amount of unused water for each seat per hour. So this number, we calculated the CASK, and we divided it by the maximum number of passengers, the plane capacity, divided by the number of kilometers, which is about 1,215 kilometers. Then we multiplied it with the actual number of passengers by the number of kilometers. So we have our objective function. Let us take, for example, the first term. The X11 CASK 1 pax means that the cost of extra burned fuel because of the amount of unused water for each passenger per kilometer on the Boeing 737-800 plane on the first departure time equals a value. So on this 133 on this different objective function terms, different plane models, different departure times, different passenger numbers, different consumption per passenger ratios. We added all this equation, the constraints, the variables, everything to an Excel sheet, and we used the solver to be able to calculate what is the optimal plane to take off on which optimal departure time, so we can minimize the amount of unused water, the amount of consumed water, the amount of fuel burn, and all of that. The results were as follows. Let us take the first Airbus 330-300 plane. So this result means that on the first departure time, it's optimal to fly the Airbus 330-300 because there is the minimum amount of unused water. So relatively, there is a minimum amount of of burnt fuel. So there is minimum amount of greenhouse gas emissions. The same thing to the 13 number of departure times. Yet now we have the optimal departure times, the optimal planes, and the optimal departure times. Now we have to optimize the amount of actual water tank fill for each plane. So we start using simulation models. We use the Monte Carlo simulation model. Monte Carlo is a simulation model that mainly focuses on random numbers. So our equations were built upon random numbers. So our models was built as you can see here. Okay, so here is the maximum water tank capacity. Here is the consumption per passenger. Here are random numbers between the maximum water tank consumption per passenger and the lowest from the data we gathered. Here is the number of passengers. These are also random numbers between the maximum capacity of the plane and the minimum accepted load factor of Egypt Air, which, as I remember, was about 87%. So here is the total consumption, which is the number of passengers multiplied by consumption per passenger. Then we divide the total consumption over the maximum capacity to make sure what is the percentage of amount of consumed water. And we rearranged it descendingly to be able to observe the extreme cases where the plane has its maximum passenger capacity and each passenger consumes the maximum consumption per passenger. And we found out that the maximum amount of water consumed was only 25% of the water tank. So we are proposing that water tanks should be filled by 30% of its capacity, leaving 5% as a safety factor in case of extra surge of demand or extra consumption per passenger for unexpected reasons to keep customers delighted. But actually, upon adding the 3 plane models on this Monte Carlo simulation model, we found out that the 3 plane models had a peak of 26% of their water tank consumed. So they were very close to each other. So the ratios were fixed. 30% is the optimal ratio for the 3 plane models flying the strip. So that was a 70% waste when we were filling the planes with 100%, and we are going to see the results of this approach right now. So on the left side, we can see the Egypt Air traditional ratios and the way they operate or apply their daily operations. On the right, you can see our ratios, the results of our approach. So Egypt Air used to have around 11 tons and a half of unused water each month. Today, with our approaches, they won't be having they will be having just 3 tons, around 3 tons of amount of unused water. The cost of extra burnt fuel because of the unused water, they used to pay around $26,000 because of this extra burnt fuel. Today, they only have to pay for about $7,000, which is much less. As for the emissions, which is the main factor, Egypt Air used to emit each month from this short trip around 20 tons of CO2 each month. Now they emit around 7 tons only for this trip. So now we are going to move on to our second approach, which is the usage of biofuel, and is it effective enough? Is it worth it to invest my money in purchasing biofuels and in making trials using biofuels? So let us start it over with general discussion of the types of biofuels. There are two different generations of biofuel. The first generation is the organic generation, the organic source generations. So the first generation biofuel most likely comes from sugar, from starch, from vegetable oil. They have organic nature, so they have huge impact on food supply, so they are not very preferred to be used globally. So we moved on and started looking forward to the second generation, which comes from different sources like green algae, paper waste, and wood. And it doesn't have a high impact on food supply, so it's a much better solution than the first generation of biofuel. So why is it better to use biofuel? Is it really worth it? So each ton of diesel or biofuel of conventional diesel emits around 2.64 tons of CO2 each hour. But for the biodiesel, you can see that only 0.3 tons of CO2 are emitted each hour. So there is a huge difference between these two ratios regarding the CO2 emissions ratios. As for the cost, which most likely we all give the highest weight in considering our investments. So the diesel liter costs around $2. The biodiesel liter costs around $0.8, so it's around 50% cheaper. Here is the important point. The diesel, when used 100% on the plane engine, it doesn't damage the plane filters or cause any harm to the plane engine filters. But the biodiesel, if used 100%, it damages the plane engine filters very badly. But why is that? The biodiesel has a very low pour point and cloud point. So on very low temperatures, when the plane is on high altitudes, the biodiesel viscosity starts to increase. It's no more pumpable. It cannot be pumped in the engine, so it affects the flight status. Also, it starts creating a wax type material around the engine filters that damages the filters badly. So it's very harmful to the plane if used 100%. So throughout observing the different trials made by different airlines, we found out that the perfect ratio to be used for the biofuel is a mix between 80% conventional fuel with 20% biofuel. So now we can save money, save a lot of emissions, and still have our plane very safe with no harm to its engine filters. So the biodiesel or the biofuel mix. What are its characteristics? The biodiesel mix has a cost of $1.75 per liter, which is much lower than the $2 per liter for the conventional fuel. The biodiesel mix emits around 2.19 CO2 tons per ton of biodiesel burned per hour. So the difference is not huge, yet it's effective. It's better than nothing, yo. So we are going with 80% of diesel with 20% of biodiesel. Back to our database. Here we can see on observation that the amount of CO2 emitted using the conventional diesel alone, they are huge. Here is the amount of CO2 emitted using biodiesel only. So you can see some real differences between the numbers, at least 50 kilograms or more each hour. So if we added it as an accumulative throughout all trips, we can get some fascinating numbers at the end of the year. So let's move on to the approach to results. Here is the total amount of emissions using biodiesel, using conventional diesel and biodiesel max. While using the conventional fuel, we were emitting through 1 month only in one short trip around 20 tons of CO2 each month. Today we emit around 16 tons that we are not applying the first approach, just using biofuel. So we already saved around 4 tons of CO2 by just adding 20% of biodiesel to our mix, our fuel. So these are the total results of the thesis. The cost of extra fuel burned as a result of unused water. So this is mainly cost. You can see that while using conventional fuel only and Egypt Air standard ratios, Egypt Air was losing around $30,000 each month. Today, while using the biofuel mix and our first approach, Egypt Air only pays wastes of around $9,000, which is much fewer than that, and it can be decreased much more than that for sure if more factors were considered and added to the equation. Here are the results, the total results, comparison regarding the CO2 emissions. So Egypt Air standard ratios using conventional fuel and using their traditional ratios, they used to emit around 20 tons of CO2 each month. Now they emit only 5 tons, around 5.5 tons of CO2 each month, which is around 15 tons of CO2 saved. Using just optimizing 2 small approaches. Imagine if we are optimizing all the operations of the airport and applying these on all planes, all plane models, and all trips. The results will be very, very effective. So, tomorrow's ideas. Here we are proposing some ideas, some helpful hints for anyone who is interested and is driven to improving and continuing the research that was started years ago and was continued by different entities from different nationalities. So this thesis handled a very short trip between Cairo and Jeddah airport. The trip is just 2 hours in time and around 1,215 kilometers. So we recommend for further research to focus on a longer trip and to add more variables. You should consider the cargo weight, the different plane models, add different models to the equation. Add the plane central gravity, the CG of the plane is a very important factor that can limit the results of the operations of this plane mass model operation. Also to be able to monitor and optimize the process in a much more accurate way, a wider scale of time should be measured, should be collected. Also, a wider number of trips should be added to the equation. So the results can be measured in a much more accurate way. Before I finish this webinar off, I have to remind you once more with the Tech Supply Chain International Conference. It will be taking place on September 19 and 20 in Mumbai. The topics are very, very interesting. Don't miss it out. You can still add your data on the comment section and someone will get and contact you with the next step. Thank you very much for your time today, and I'll be very, very glad to receive any questions regarding our topic. And thank you very much for your time.
So thank you, Filos, for the insightful presentation. Now moving to our Q&A questions, we have a few questions from the audience. So one of the audience is actually asking if you can constrain part one for slide 21. So can you get into details on the slide 21?
Okay, give me a moment. Slide 21, okay. Okay. So,
We lost.
yeah, I'm with you. I'm sharing my screen. Give me a moment.
I think it was the graph, if I'm not wrong. So it's the constraint graph, slide 21.
Okay. Which constraint?
Just
Here?
can I see? I'm checking. Just hold on.
Okay, take your time.
Yeah. So it was the slide for the objective function. You know where it says you minimize the cost. Yes, this is the slide. This is the slide.
Yeah,
Yes.
okay.
So they want to know. Can you just explain this slide again once?
Okay, sure. So,
Yes.
our objective function was to minimize the cost of extra burned fuel. That is resulted because the extra weight, because the amount of unused water on the plane trip. So we created a term called XIJ cask. The X is the variable, is the value of the cost. So the IJ and the cask are just specifications of this coast, characteristics of this coast. So the I refers to the fleet time. The J refers to the fleet type. So the XIJ alone means that the cost of the first plane model on the first fleet type equals a value. The cask means specifies the characteristics of this cost. So when we add the cask to this term, it means that the X now means that the cost of amount of burned fuel because of the amount of unused water per seat per kilometer for the first plane type for the first plane for the first departure time equals a specific value. So the IJ and the cask just refers to the specification of the cost, which is the X. Okay. So I hope I answered your question.
All right, perfect, Ilos. So there's one more audience asking
Okay.
you that information technology is setting a strong foundation manufacturing in aviation.
I didn't hear the first part of the question, please.
All right, let me repeat. It's like how information technology
Uh-huh.
is foundation in
Okay.
manufacturing in aviation.
Actually, that's a wonderful question. The IT has a very, very important role actually in green aviation future. Here is just a small trial, just small proposed trial. There should be IT systems that you just before the plane depart, you add the number of passengers, it calculates and predicts the amount of consumption per passenger, so it can just predict which is the optimal amount of water to be filled, which is the optimal amount of weight distribution in the plane, so we can minimize always in all our trips the amount of extra burn fuel and extra greenhouse gas emissions. Also, there can be softwares that can optimize the daily operations, the loading and the unloading, the operating time of the plane on the ground, the departure time, the landing times, everything can be optimized using softwares. It will ease the process a lot, and it will help us receive some really fascinating results from this sector that it has insufficient progress until now. But I believe that it's not going to stay like that for too long. Okay. So I hope that I answered your question too. Actually, as well, the investing in the IT softwares and investing in research-based, IT-based researches and projects adds a lot to the company. As you can see here, we invested just 1 month from our time and few starting budget, and we created a real observed difference with real results. So we hope that companies can invest in IT-based projects and start to invest in optimizing their daily operations. They will save costs, so the cost-benefit analysis would be on their side, and they will keep our planet green and improve the status of the aviation sector, specifically the greenhouse gas emissions of the aviation sector.
All right. So there's one more audience. He's asking,
Okay.
what basic principle aviation companies should follow in order to improve energy, resource efficiency in aviation manufacturing and air transport, and to create a clean energy system?
Okay. So mainly, we have to be able to know what are all our operations that are made every day, and to categorize these operations according to the amount of CO2 or generally the greenhouse gas emissions emitted from each operation, and we arrange them descendingly. So we can start from the most inefficient operation, and we start studying it, the way we are doing it, and how can we optimize it. So mostly operation research math models will work perfectly in solving such problems. Optimization math models, such as the simple ones that we introduced today, in a wider scale with different number of constraints and a wider, much wider amount of data. These can easily help optimize these problems. There are actually different problems in the airport other than the water tank capacity. Planes can stay on the ground waiting for the passengers to get boarded for an hour maybe, or minimum 30 minutes. So this time the plane engines are operating for no reason at all, so that the air conditioning can still be working. This burns a lot of fuel without even being noticeable. That's why London Heathrow added electrical units and preconditioned air to the airport landing area, so the plane cannot be started on ground for no reason, to save the amount of extra burn fuel. Also, the weight distribution with considerations for the plane's central gravity. If the weight is distributed in a perfect way, the plane will fly in a more smooth way. If we are considering also the speed factors, there is an optimal speed factor. You can find the references in the presentation, where you can follow the research made by the Chinese and the Indian researchers. They discussed these factors in more details, specifically the speed factor. The altitude plays a very important role in this equation. So if you go very high, the plane has a much higher resistance, so the engine burns extra fuel. So it's a very, very complicated equation with a huge number of variables, huge number of constraints. Actually, we can reduce the weight of the plane by reducing or replacing the type of materials that the chairs and the plane body are made of. Also, while considering the CG of the plane, we doesn't have any opportunity to ruin it or to affect it by any means. So there are actually different ways to optimize these operations. Actually, reducing the amount of extra weight on the plane may add an opportunity to add extra cargo on the plane, which will generate profit. Yet we are not 100% sure this will be profitable. Our extra weight, our extra cargo may result in losing extra expenses per hour, which might be more than the amount of revenue that's coming from it. So everything should be calculated in details using professionals. Everything should be observed. Every factor shall be considered. A wider time scale should be covered so we can measure seasonality, we can measure surge, demand surge, or any extreme cases, so we can be prepared for all scenarios. Aviation sector has no chance for any error percentage, so we have to be as accurate as possible.
So, Kiros, thank you so much for your invaluable insights on this industry, and thank you everyone for joining us in the webinar. So it was a really good one, and I hope we have many more coming up. So see you again in our next one.
Thanks a lot.
All right. Thank you so much.
Thank you.
All right.